When we talk about threaded fasteners, what we are actually referring to is an assembly of parts that work together. These parts are the bolt, the nut, and in some cases, a set of washers. The bolt is the primary load-carrying element of the assembly. It consists of a bolt head and shank, where a portion of the bolt shank is threaded. The second part is the nut, which is a structure that contains a mating set of threads that interlock with the threads on the bolt. The last parts are the washers. These are annular plates typically made of a very stiff material which help spread the load acting on the bolt head and nut over a larger area. There are a number of pros and cons to threaded fasteners to consider when designing a joint. On the pro side, threaded fasteners can be made out of a wide range of materials, including both high-strength and low-strength metal alloys. This provides a designer with a wide range of options in selecting the best performing fastener for the job and to tailor fasteners for different roles, such as tension or shear dominated joints. Another pro is that threaded fasteners are able to generate large clamping forces. This is particularly important for tension type joints and for joints that serve a sealing purpose, where leakage of fluid, such as fuel, could occur if the parts are not sufficiently clamped together. Threaded fasteners are also removable, making them ideal for applications that require the joint to be disassembled in service. Disassembly could be necessary for maintenance purposes, such as replacing a damaged windshield in the cockpit of an aircraft. Moving to some cons of threaded fasteners, the fact that they are removable can also be a negative attribute. During operation, loading and vibration can cause threaded fasteners to become loose and even fall out. For this reason, threaded fasteners are typically wire-locked in aircraft applications. Wire locking is a process whereby a wire interlocks adjacent fasteners in such a way that loosening of one fastener would result in tightening of the adjacent fasteners. Wire locking certainly increases the cost of a mechanically fastened joint in an aircraft, but the fastener itself is also costly relative to standard aerospace rivets. Threads have to be accurately machined in both the bolt and the nut to ensure a good interlocking fit. This is in stark contrast to rivets, which we will look at next. Aerospace rivets look similar to a standard bolt, but without the threads. Rather than using a thread and a nut, the end of the fastener is plastically deformed in order to create a permanent connection between the joint parts. Rivets can come with a variety of head styles and can even come in the form of rivet wire, where both heads of the fastener are formed during installation. Rivets overcome many of the disadvantages of threaded fasteners. They are extremely cheap, not requiring any additional machining steps to produce the fastener itself. This can be a significant overall cost factor when you consider that a modern commercial aircraft can contain millions of fasteners. Rivets also form a permanent connection that cannot vibrate loose, negating the need for costly wire locking of the individual fasteners. Rivets also have some additional performance benefits that we will look at momentarily, but let's first discuss some of the cons of riveting. The range of materials that can be used for rivets is rather limited. Because riveting relies on plastically deforming the fastener itself, we are limited to lower strength and highly ductile materials. As a result, rivets tend to be significantly weaker than threaded fasteners, limiting their use in certain applications. The strength of a fastener is not the only consideration in the design of a joint. When we produce a mechanically fastened joint, we first need to drill holes in the structure. And as we saw earlier in the course, adding a hole to a structure introduces a stress concentration which will weaken it. But rivets have a unique way to compensate for this weakness. They expand to fill the fastener hole. Let's look at the rivet installation process step by step for the case of two thin sheets being joined and try to understand the benefits of hole filling behavior. We will look at a top view of this process on the left and a cross-sectional view on the right. First, a rivet is inserted into the holes drilled within the two thin parts being joined. As seen in the illustration, the size of the hole is actually larger than the rivet, making it easier to insert the rivet during this step. With the rivet in place, it is possible to begin the next step. In this step, compressive forces are applied to the rivet through either squeezing or hammering. This action causes the rivet to expand, first elastically, then plastically, filling the fastener hole. As the fastener hole is filled, the rivet begins to apply a pressure on the inner surface of the holes in the sheet. Further compressive forces cause the formation of the deformed rivet head. However, it also results in plastic deformation within the sheet, highlighted here in blue. In the final step, the rivet installation force is removed and the sheet tries to relax, just like when a rubber band is unloaded and shrinks back to its original size. But due to plasticity, the blue region around the fastener hole will be larger than it originally was. The surrounding sheet will thus compress the plastic region, trying to push it back into its original shape. This final state leaves the material around the rivet hole in a state of residual compressive stress, which helps reduce the stress concentration. Residual compressive stresses are not the only fatigue beneficial outcome of hole filling in a riveted joint. Recall that the stress concentration factor of a hole in an infinite sheet is approximately equal to 3. Stretching of the material under this load also causes it to deform into an oval shape. The situation, however, changes if that hole is filled. The ovalization that previously occurred is restricted by the rivet, resulting in contact forces between the rivet and the hole surface, which redistribute load. This causes a reduction in the stress concentration factor to approximately 2 for the left and right-hand sides of the hole. The ovalization shown here is greatly exaggerated, so even small differences between the fastener diameter and the hole size can result in the higher stress concentration factor. So the hole-filling nature of rivets is critical for obtaining this benefit. Tension loading within the plate is not the only loading affecting the stress concentration around the fastener. The fastener itself will introduce a pin loading into the sheet that we refer to as bearing. This bearing load transfer also has its own stress concentration factor that we need to consider. If the fastener hole is unfilled, load transfer between the rivet and the sheets only occurs on one side of the fastener hole. This concentrates the load in the sheet, resulting in a large stress concentration. If the hole is filled, the fastener begins with a radial compressive load acting all around it. As the bearing load is added, a reduction in radial compression on the lower half of the hole and an increase in the radial compression on the upper half of the hole transfers this load. Thus, the load transfer is spread over the entire surface of the hole, reducing the stress concentration factor. So to recap what we have seen, mechanically fastened joints can be classified by the type of fastener, threaded fasteners, rivets, blind fasteners, and nails, and by the primary means by which the fastener transfers load, tension and shear. We examined in more detail threaded fasteners and rivets, highlighting some of the main advantages and disadvantages, and why riveting is still commonly used in the aerospace industry despite the fact that drilling holes in a structure will generally weaken it. Ultimately, the design of a complex structure requires a series of compromises.